Hello and welcome to Basins and Beer with ESA Analytics. I'm Blue Spikes. Today I'm going back to the Williston Basin to discuss a new feature that we've just released, which is a reservoir model. It'll help users find sweet spots where they can expect to see the best returns. I'm going to be drinking Palisade Peach Wheat by Breckenridge Brewery. It's a 5.3% with an IBU of 14, so super smooth. If you know anything about Colorado, and you've been out to the western slope, you know they grow peaches out there. They're really great, and so there's a lot of products in Colorado that contain these Palisade peaches. I like wheat beers that have a little bit of a fruit taste, especially if it's not sweet, and so this is a very good one. I've tried it before, and it's just in time for all the warm weather we're having. We hit 80 degrees today, which is just amazing. So anyway, if you haven't tried this, get out there and try it. And obviously go enjoy the warm weather. That is so good. All right, if you've been following these videos, you know that I've taken the last month off, basically. Not that I haven't been working, but I've been focused on this, the development of this reservoir model. It has been a lot of work, but the fact that we can now provide a reservoir model for any basin, anywhere, without the need for a lot of specialized petrophysics and give a very good result is really just amazing. I don't think there's any other platform out there that can do anything even close to this. So I hope you'll jump in here and try it. I can tell you right now we've really got the Three Forks and Middle Bakken in the Williston Basin dialed in. And I'm going to be updating every week basins to get into the primary producing formations, and then we'll start to go back and get more secondary formations. Again, I say we don't need a lot of petrophysics. We do, however, need to have triple combo logs and really good top picks in order for this to work. Otherwise, it all falls apart. So that's what we're doing right now, is we're going through and cleaning up, because once you get to the analysis phase, you know, your data's got to be that much cleaner. And so that's where we are with our product. We're to the point now where we can really start to do full-on basin analysis, including reservoir modeling. So let me jump into the Williston Basin. If you've seen my videos before, you know you just pick your basin and you're off and running. It takes a couple seconds to load, because there are about 50,000 wells. And I usually tell you to color by formation. I'm not going to tell you that this time, because I know where I'm going, and I'm going to focus on the reservoir model. So we have thickness data for every formation that is currently being what's called memoized, so that it's available quickly within the application. I was hoping it would be ready for this presentation, but it's not, so it should be ready overnight. So instead I'm going to show you the Bakken middle, the TVD subsea, or the depth to that formation. And the reason I want to show you this is this feature that appears. Well, first of all, it shows you that there's two lobes. You have the Nesson anticline that splits it right down the middle, and you have the Missouri River that splits it from west to east. But these are features that help you kind of orient yourself with this basin. You can always focus on this giant turn in the river and know that that corresponds with the middle of the Nesson anticline, and that will help you sort of locate the core acreage in this basin. It's always centered right on this area. So with that, I'm going to jump right into the V shale. So V shale is a measure of how much shale there is in the formation. So it's as a percent. I'm going to go ahead and color by here real quick too. I'm just going to color by TD. It'll just make the dots a little bigger and easier to see. So the V shale is a measure of how much shale there is in the formation. And in this case, so it's measuring percent of V shale for the middle Bakken. So you see it's really low in this area. Let me open the sidebar so you can see a distribution of this. And let me always remember to do the average. So this is the lowest V shale, and that's if you know how V shale is calculated, it's primarily with gamma, and so this gamma is really low, which means it has really low V shale. So that helps this be really, in the end, you'll see that this is good reservoir, primarily because the V shale is so low. But everywhere else, for the most part, you see it looks pretty consistent. If you're down here, you're probably looking at maybe, 7% V shale. As you move north and west, it increases all the way up to, here you're looking at 24% V shale. You see kind of the median, or at least the most common V shale is around 15%. So somewhere in here is kind of the middle. So the V shale is important because if you have too much V shale, you're going to have difficulty fracking the well, and you don't have a very good reservoir. So that's why lower V shale tends to be better reservoir. But it doesn't mean you have to have zero. It just needs to be on the lower end. As soon as you get really high V shale, you start to not be able to get the oil out of the ground, even if it exists in the pore space. So now we'll look at kind of the next measure, which is porosity. So this is called phi. It is a combination of your density porosity and your neutron porosity. And the density porosity comes from your bulk density, and then you do a correction based on the V shale. So if you see up here, this is your best porosity, but you also remember this had the lowest or the highest V shale. So you can bet this, this could be a good reservoir, but you can be sure that it probably isn't, just because the porosity is high, but the V shale is high. In this area, we had high or really low V shale, but here the porosity is sort of in the middle. And down here you have, for example, about 5% porosity. Up here, you might be getting into that 7%. This is almost 8%. So like the range of porosity, you can see, is not that wide. It's very important. These small increments matter a lot. But here you're talking about, this most common number is around 5%. You start to get up to 7 or 8%. Now you're into rarefied territory. So it's just kind of amazing how a small change in porosity really makes a big difference. So the next thing we're going to look at is reservoir quality. So this one's always a little bit harder to interpret in a map, I think, because there are so many factors. So reservoir quality is a measure of porosity, permeability, grain size. A lot of different factors go into your reservoir quality. So the fact that we have anything that looks really clear, this was that really low V shale area. Everything else looks like a little bit more of a mixed bag, but you have really good reservoir over here. You have good reservoir in this area generally, and then it's okay in this area, it's okay in this area. So again, this is a measure of permeability and porosity primarily, but also other factors like connected porosity and grain size. I think I already mentioned that, but there are a lot of factors that go into reservoir quality. The next thing we'll look at is HC-sat. So this is your hydrocarbon saturation. So there are two types of saturation. There's your water and there's your hydrocarbons, at least in terms of oil. So if you're looking at a map like this, this is where you start to see a really good pattern. Again, this is good saturation. This is meaning, up in this area, you have 70% or better hydrocarbon saturation, which means you have low water saturation. So if you have 70% water, you have 30% hydrocarbon, and vice versa. So your best areas, you can start to see your best reservoir is really here, and here's that Ness and anticline, and of course your river cutting through, and then over here. So that's interesting. You can see all of a sudden, even though there was some good porosity up here, this starts to fall apart. It's not, it takes all of these different properties to line up to make a good reservoir. So we go to the BVH. So this is our next to highest level product. This is your bulk volume of hydrocarbons. So this is your percent of hydrocarbons. So this would be within the Bakken formation, or the middle Bakken specifically, the percent of hydrocarbon per volume. So over here, your high numbers are in this sort of, 5% or higher. Your low numbers are less than 1%. So again, we get to these really fine differences between what is acceptable. In this case, 2% is acceptable, right? That is rock that's probably economical. Obviously depends on your different economics, but generally speaking, 2% is a common cutoff. Anything above 2%, you're getting into really good reservoir. And so over here you have good reservoir, over here you have good reservoir, and all of this is sort of your marginal stuff, but probably worth at least putting a hole in the ground and exploring. The final measure is really where it's at. So this is your HHC, or your height of your hydrocarbons, or your thickness of your hydrocarbons. So at this point, we're multiplying your bulk volume of hydrocarbons by your thickness, and we're getting your total thickness of the formation that is hydrocarbon saturated. And so this is in feet, which is kind of cool. And so of course your thicker areas with a lot of hydrocarbon saturation are your best areas. So all of a sudden now you start to see the real pattern, because yeah, this is low V shale, this is good reservoirs, a lot of good things going on out here, but it's thin. So you don't actually have that much oil. I mean, you have good oil. I mean, this is a good producing area, but you get over here, this is where things are really great. And that's because you have good properties and you have a thick reservoir. So you start to put it all together, you can see this is your really great area. This is a secondary area. And then, this is all more marginal. And you get out here into these blue areas, and those are do not drill. You don't want to be out there. So the next thing I want to do is show you how to compare this to actual production, to see how do we do. This is our reservoir model, so how does this compare to actual production? So we can go to your bulk volume, the HHC, middle Bakken. Adjust my binning size. I know because I've done this a few times, this is a pretty good number in terms of actually mapping it out. Okay, I can turn off my dots and turn on my aggregated layers, and I have to remember to do the average. So this is your per well average instead of your cumulative amounts. So you can see, sure enough, what this is every point within this square is now averaged, and this is sort of your sweet spot, and this is your sweet spot. And you can see over here, everything that is sort of yellow to red is good reservoir. So this is good reservoir. Now notice it doesn't pop as much as this area, even though in a lot of our maps this looked amazing. But again, that's because it's not very thick. So over here, you can see this is your core acreage, like especially right around this bend in the river, right along this Nesson anticline. So to prove to you that this is an accurate map and that this method worked, I'm going to now show you production. So go to production, do oil 1 year, just so we're looking at sort of a common measure of oil production. So this is how much oil was produced in the first year of each well. That way, a well that was producing for 20 years isn't overrepresented versus a well that only produced for 1 year. right now, let me turn that off just so it doesn't get too confusing. So this is what that looks like. But this is for all formations. So, and verticals and horizontals and everything else. So I'm going to boil this down to Bakken only. And I'm going to look at only horizontals. Because then you can start to just say, these types of wells in this area, targeting this formation, this was the production. And that's a fair comparison because we're looking at reservoir specific to the middle Bakken. Okay, so this is what it looks like. Sure enough, again, so you have, this is that big turn in the river right here. Sure enough, this is your best reservoir. So let's see how we did in terms of an actual comparison. So if I turn on my, so I mean, you can look at this. This is, you know, they're getting pretty good oil production out here, but it's nothing like what they're getting in this area. So if you zoom in, you can see this is good, and they are, you know, they are getting, you know, this is good reservoir out here, but it's really not as good as the core. So let's zoom in on the core here. Just so you can get a sense of what does the background map, which is your reservoir quality, look like compared to your actual production. So your best production, of course, is the reds and the yellows. And so just looking at how that compares. So this is, again, a reservoir model based on logs with no petrophysics. But, I mean, honestly, to me, this is a great representation that we can do this work in this kind of application quickly, accurately, and give you really great results. So that was my presentation on that. I want to give a shout out to Paul Devine. He's a retired geologist who lives in Denver. He reached out to me and said he had this really great model that can help you identify sweet spots in these types of basins without the need for advanced petrophysics. And he convinced me to give it a go and see what it would look like, and I'm very happy with the results. I think this is a great solution for this kind of big data, we're looking everywhere sort of model that we're applying with our application. If you're interested in how this works, or you really want to know the details, you can go to LinkedIn. You can look up Paul Devine. He's released a ton of information on it, PDFs, examples. I mean, he's happy to share this and show that, you know, this is a way that a lot of companies have evaluated acreage over the years, even though, you know, we've all kind of assumed that, oh, they're doing petrophysics and that's all they do. Well, it's not true. I mean, a lot of what they do is this kind of approach because they need to look over such a big area that they can't spend all the time and energy and effort looking at petrophysics for just small areas. They have to really look in large areas to figure out where to sort of refine their search. So he's a very good guy. I'm very happy that he reached out and helped me put all this together. So anyway, thank you, Paul. Thank you all for tuning in. Until next time, cheers.